Modern intrusion detection systems operate in an environment of ever-increasing complexity, so analysts are faced with enormous volumes of network events, high log generation rates, and increasingly complex techniques used by attackers. Traditional ideas are mainly based on signatures, static rules. This makes them effective against known attacks, but vastly limits their ability to detect new, modified, or deliberately hidden threats. In addition, such systems often generate a large number of false positives, which overloads analysts and increases the risk of missing a real attack. To explore the potential of machine learning to improve threat detection, the project used three different datasets. Dataset A contains network and behavioral parameters of user sessions, such as packet size, number of failed logins, IP reputation, and access time. It was used to train a binary model tasked with distinguishing between benign and malicious behavior. Dataset B consists of text reports of incident investigations, including description of attack scenarios, techniques used, tools, and consequences. This set was used to build a multi-level attack type classification model. Dataset C is completely separate test sample that simulates real data and is used to test the entire ML pipeline. The approach I have developed is based on two sequential models. In the first stage, the system analyzes network characteristics and determines whether the activity shows signs of being malicious. This allows it to filter out a large streams of events and highlight only those cases that require further analysis. Second stage, a deep classification model, uses text descriptions from data B and determines the specific type of attacks based on TF-IDF text representation and structured features. Essentially, this simulates the automated event processing flow in a SOC. First, the model performs screening and identifies incidents that pose a real risk. Then, the second model helps to quickly determine the attack technique and form an analytical conclusion. This two-stage pipeline combines the advantages of structured network data and rich text descriptions, providing a deeper and more contextual understanding of the threat at hand. As part of the binary intrusion detection task, I developed a model that makes a difference between benign and malicious sessions. First, I studied the dataset A. I checked the structure and absence of gaps, the balance of classes, and distribution of features. The most important feature in fusing the model's decisions are the number of login attempts, the number of failed logins, IP address reputation, network packet size, and access at unusual times. These parameters directly reflect the characteristic behavior of attackers. For pre-processing, I encoded categorical data, scaled numerical features, and used class weight balance so that the model would correctly account for rare attack cases. I trained several algorithms, logistic regression, KNN, MLP, and random forest, and compared them in terms of accuracy, precision, recall, and F1 score. Random forest turned out to be the best model thanks to its high F1 score and near perfect precision, which reduces the number of false positives. It's also easy to interpret, which is important for cybersecurity. There are still limitations. The model might be vulnerable if an attacker deliberately changed their behavior to look like a normal user or uses the new techniques that are not presented in the data. Therefore, such a system needs to be regularly updated and monitored. Overall, the model effectively identifies known types of malicious sessions and is suitable for use in POC. In the second part of the project, an attack classification model was developed based on dataset B, which contains text descriptions of incidents, techniques used, additional structured fields. During the pre-processing stage, the data was cleaned, gaps were filled, and all text components were combined into a single field. The text was converted using TF-IDF, and categorical features were converted using one-hot encoding, which allowed different types of data to be combined into a common set of features. Both traditional models, naive Bayes, logistic regression, random forest, and a deep MLP neural network model were trained for classification. The evaluation was based on accuracy, precision, recall, and F score. The MLP neural network showed the best results, about 82% accuracy and 0.72 macro F1, outperforming other models. This is due to its ability to capture complex patterns in long text and high-dimensional features. Error analysis revealed that model often confuse attacks with similar descriptions and identical meter techniques. Dataset limitations, severe imbalance, and text similarity also affect classification quality. In a real environment, such errors can lead to incorrect COC playbook selection and response delays. As a result, the most suitable solution for POC was the MLP model, which provides the data most stable and balanced attack classification. In the first part of the task, I integrated both models, the binary detector from task 1 and the attack type classifier from task 2, and applied them to the dataset C. First, I reproduced the same pre-processing used in task 1, the same categorical features, and the same one-hot encoding and scaling with the same scaler. After that, the binary model classified each session as benign or malicious. The results of part 1 was very strong. The model achieved 97.4% accuracy with a recall of 0.9 and precision of 1.0 for the malicious class. Out of 954 sessions, it flagged 412 as malicious, which became the input for the second stage. In part 2, I applied the attack classification model only to flag sessions. It's important to note here that dataset C contains many new types of attacks that wasn't presented in the training dataset B. There were a lot of these new types. Out of 412 malicious sessions, only 40 contained an attack type that the model had seen before. It was on these 40 known examples that the model demonstrated high quality, about 95% accuracy and 0.93 macro F1. This is quite expected. The classifier works well with attack models it's already known. Main conclusion of stage 3. Machine learning pipeline reliably detects malicious sessions, accurately classifies the type of attack, but only between the classes that were presented in dataset B. In a real SOC environment, this means that the model needs to be updated regularly so that it can correctly process new or array types of attacks. Despite this, the overall prototype works stably and demonstrates good suitability for practical application, provided that it's periodically retrained. The introduction of machine learning into cybersecurity opens new opportunities but also poses serious risks. One of the main risks is vulnerability to aggressive attacks. An attacker can deliberately change network activity parameters or report wording so that the parameters appear safe to the model. Such manipulations can completely bypass machine learning detectors. The second important aspect is classification errors. False positives increase the workload on SOC analysts and lead to alert exhaustion, while false negatives can mean missed intrusions. For critical systems, this can have direct consequences for the security of the organization. Another risk is a concept drift. Attack tactics change rapidly, new techniques emerge, and model trained on old datasets gradually becomes irrelevant to the current threat landscape. Results on dataset C demonstrate this in practice, where most attack types were unknown to the model. To mitigate these risks, regular model training, quality monitoring, false positive control, and mechanisms for handling unknown attacks, such as the unknown class, are necessary. In addition, human validation of critical incidents and backup rules for safe behavior are important. These measures make machine learning solutions more reliable and ethically safe in a real SOC environment. Okay, so first I load dataset C and check its size. It contains 150 records. To bring it to a format similar to the first task, I remove the session ID column because it doesn't contain a useful information for the model. Then I check if a dataset has an attack detected field to save the true labels if they are presented. Next, I perform one hot encoding of the same categorical features that were used to train the binary model, protocol type, encryption used, and browser data. Browser type. As a result, we get 37 features. After initial feature encoding, there are more features than were in the model during training. Therefore, I'm aligning the data structure using the array index method. I leave only the columns that were in dataset A and fill in the missing ones with zeros. Now the dimension becomes 954 by 13, which completely matches the dimension expected by the binary model. So the next step is to scale the data using the same standard scaler that was trained on dataset A. This is important because the model expects the data in the same numerical scale. I apply the scaler and obtain a final feature matrix of shape 954 by 13. Now I apply a binary model to determine whether each session is malicious. The model returns both binary labels and probabilities. I store them in a data frame. From the first few lines, we can see that some sessions are marked as malicious and some as normal. If dataset C contains true labels, I can evaluate the quality of the binary model. The error matrix shows excellent results. There are no errors for normal sessions. 517 out of 517. The model is also very accurate for malicious sessions, 412 correct and 25 erroneous. The overall accuracy is 97%, which is confirmed by high precision, recall, and F1 for indicators. After binary classification, I filter only those sessions that the model has flagged as malicious. There were 412 sessions out of 954. This data becomes the input for the next stage, classification of the. So at this stage, I begin preparing data for the second model, the one that determines the type of attack. I will fill in the gaps in the text and category columns and then combine all text fields into a single column called combined text, as I did when I trained the model with dataset B. After that, I perform a set of features to feed into the model the combined text and the categorical fields, category, target type, and meter technique. So now I feed the prepared data from malicious sessions into the attack classification model. The model returns numerical classes, which we convert back to string names of attack using label encoder. We write these predictions to a data frame. To evaluate the quality of the second model, I only keep those malicious sessions where the attack type is present among the classes known to the model from dataset B. There are such only 40 sessions. I perform a quality analysis on them. The final accuracy is 95%. Most classes are identified perfectly with an F1 score of 1. Minor shortcomings arise only in rare attacks where the sample size is minimal.